Okay, welcome to lecture here. We're going to continue on with chapter 5. We're going to finish that up, and then we're going to roll into chapter 6, I think. Again, the notes for chapter 6 should be up online if you need them. Good stuff here. Just move a couple things around here so I can actually see. All right. Okay, so we've been talking about chapter 5. In chapter 5, we were talking about some important sort of conversions, grams to moles. And again, to do that, we use the molar mass from the periodic table. We also talked about Avogadro's number, which is that 6.022 times 10 to the 23 number. And that represents how many atoms or molecules there are in 1 mole of something. And again, doing that grams to moles or moles to grams conversion using the molar mass from the periodic table is a very, very common sort of conversion that's used a lot. To get the molar mass, we basically add up all the parts to the formula from the periodic table. And again, it's those numbers that are underneath the symbol. And when we do take those numbers, that represents how many grams there are in 1 mole of that substance, one formula basically of it. We also talked about balancing equations and different types of equations or reactions. And we then talked about last time really putting both of those things together, taking a balanced equation and doing conversions like grams to moles or moles to grams to figure out, if we started with a certain amount of reactants, how much products we could produce. We also could figure out if we know how much products we produce going the other way, figure out how much reactants we started with. We can also stay on the same side of the arrow if you want and figure out, if we know something about one of the reactants, we could figure out how much of the other reactant we need to put in there. And if we know something about the products, we could do the same thing. We can figure out how much of the other product would be formed in a reaction. When we do these stoichiometry problems, which is what we talked about last time, really there's 4 basic steps that we talked about and that we saw sort of over and over in those examples. The first and most important thing is you always want to start with a balanced equation. So if the equation is given to you, you want to make sure that all the coefficients are correct and that it is balanced. And the reason we do that is because when we look at the coefficients in a balanced equation, that represents the mole to mole relationship. And that gives us really the conversion factor that we need. And that really is what stoichiometry is. Again, as we talked about, it really is nothing more than just a conversion factor. And where you get the conversion factor is from the actual equation rather than go to a table and basically look those things up. So we can find that mole to mole relationship by doing that. And the reason we need to kind of follow those steps is to make sure that everybody's in the right units. So once we get the balanced equation, we want to take whatever they give us and convert it to moles. And a lot of times that may be in grams, and you need to use the molar mass from the periodic table to convert grams to moles. Once you have it in moles, then the third step is to go to the equation and find the 2 things you're interested in. One thing is whatever they gave you, and the other thing that you're interested in pretty much in this class is what you're trying to find. And you can find that mole to mole relationship from the equation. And again, that allows you to get 2 conversion factors like we talked about last time. And really, it's just going to allow you to go from one substance in that equation to another. And that's a sort of a conversion factor to allow you to do that. The 4th step is, and again, sometimes you may need to do it or may not need to do it, is you will always be in moles after you do the 3rd step. And because of that, you may need to convert those moles back to grams or some other unit. And again, sometimes you need to use the molar mass on the back end of the calculation to really kind of convert it back into something like grams. We saw that you could do each of those steps sort of individually and get answers along the way. And as we talked about, if you do, you then want to make sure that you don't round too much until the end. Or you could do all the steps all at once, all the way across, and kind of get the answer at the end. So either way is fine. The important things that we talked about is you want to make sure, again, equation is balanced. And very common, people mess up when they do the molar mass because they see the balanced number or the coefficient in the equation. So when they go do the molar mass, they sort of insert that in while they're doing it. So a reminder that if you go to the periodic table and you need to look up or figure out the molar mass of a substance, You essentially just take the formula by itself and add up all the parts, regardless if there's like a 7 in front of it in the balanced equation or an 8 in front of it in the balanced equation. That has no effect when you're going to calculate the molar mass from the periodic table. It should be done just basically solely off of the actual formula that you see. Any questions on any of that stuff we talked about last time? Okay, then we're going to finish up this chapter. We're going to talk lastly here about chemical equilibrium. And chemical equilibrium is an idea when we have a certain type of reaction. And usually when we have sort of a chemical equilibrium happening, the type of reaction we have is what is referred to as a reversible reaction. So typically we have, say, A plus B goes to C plus D. And this is a reversible reaction, which means there's really two directions. And that's why we see these arrows that head in both directions. And there's the direction where we go from reactants to products, which is sometimes referred to as the forward direction. And then there's, in this reaction, at some point, the products will actually head back the other way. And the products will go back and make some of our reactants. And that's what's referred to as the reverse direction. And when we say that something has come to equilibrium, oftentimes people misunderstand what that means. A lot of times people think that when we come to equilibrium, what that means is that we have the same amount of, say, reactants and products. So the same amount of everybody on both sides. And that's really not what equilibrium means. So when something reaches chemical equilibrium, what it actually means is the rate of the forward reaction will equal the rate of the reverse reaction. So what that means is just as fast as it goes to the product side, those products are going to come back the other way. And what that means is whatever the concentrations were of our reactants at that point, and whatever our concentrations were of our products at that point, they essentially will maintain those concentrations. So for example, if A was, say, 4 at that point, and B was 2, and C was 3, and D was 5 molar or something like that. What that means is when this reaches equilibrium, A will be able to stay at 4, B will stay at 2, C will stay at 3, and D will stay at 5. Again, they'll go back and forth just as quick as they can, and nothing will essentially change. So just as quick as you go one way, the other way comes back, and it sort of levels out and remains sort of constant all the way through. So when we talk about equilibrium, that is what we're talking about. Again, doesn't mean that we have the same amount of everybody on each side, but it means that as fast as it goes to the product side, those products will recombine and go back the other way and make our reactants. And again, essentially what that does is pretty much locks everybody into place. Now, there's a sort of relationship known as the equilibrium expression, which is K, capital K. These arrows miss the equation there, or a little bit. We'll put them in. Those guys obviously should go up there. They're close. And there is a relationship which is known as the equilibrium constant, capital K. And capital K is the equilibrium constant, which is essentially the products divided by the reactants. And when we see a little box like this, this means concentration. And when we talk about concentration, we're usually talking about capital M, which is molarity, which is moles per liter. So that's molarity. So what we do is we take the concentration of our products, so that's C and D, and we take them to their exponents, which is the coefficients, and we divide it by our reactants. So basically it's products over reactants. And K is actually just a number. So K doesn't really have units, it's just a number, but the number does tell us something. If we have a large value of K, if K is large, what that means is when we reach equilibrium, we would mainly have products. And again, just mathematically looking at it, if you have a large number on top divided by a small number on the bottom, you will get a large number. And that's how come we could figure out that we would mainly have products. Now, if we had a small value for K, what that means is when we would reach equilibrium, we would mainly have reactants. Same math there. That would mean that we have a large number on the bottom, smaller number on the top. That gives us a small number. And that means that when we reach equilibrium, we'll mainly have reactants. So you may ask yourself, what's a large number? What's a small number? The big number of 1 basically is a large number. So anything above 1 is considered large, which means if you have an equilibrium constant value given to you, you could probably safely assume that when it reaches equilibrium, products will be mainly formed. And if you have a really small value of K, anything less than 1, it's assumed that you will pretty much have just reactants present. Any questions on that there? All right. Now, when we do have a system at equilibrium, we have something which is known as Le Chatelier's principle. And Le Chatelier's principle is when we do have this system that's at equilibrium, essentially we have this reaction. It's going to go back and forth at the same rate. It is at equilibrium. We're going to do something to this reaction. We're going to add what is sometimes referred to as a stress. And stresses can be concentration. It could be pressure and volume. It can be temperature, maybe a catalyst. And what happens to the system that's at equilibrium is when we add a stress to it, what we essentially will do is mess it up. So we add a stress, we mess up the equilibrium. And basically what that means is at that point, when you do that, you no longer have the rate of the forward reaction equal in the rate of the reverse reaction. So what's going to happen is it wants to get back to equilibrium. So what this reaction will try to do is return back to equilibrium. And there's really 3 sort of options that can kind of help it do that. It can shift to the right. And when we say the reaction shifts to the right, it basically means we need to make more products. The reaction can shift to the left, which means we need to make more reactants to reach equilibrium. Or the third option, as we'll see, is there could be no change. So it will not really shift either way. It will not make a difference, depending on what you do. There really will be no overall difference that's going to occur. So let's talk about each of these sort of stresses that we could do to a system and sort of what happens and how we could look at it. So let's take a look at this here, I think. Okay. So let's first take a look at concentration. So concentration is not too bad. You could pretty much do 2 things with concentration. You could either add more or you can remove. So let's talk about what happens when we add more concentration. So when we add, what happens to the equilibrium is it shifts away from the side we added it to. So if you add a more reactant, it will shift away to the products. If you add more products, it will shift towards the reactant side. So add away, AA is a good way to remember that. The other thing that you could do is you could remove. And when we remove, basically you will shift towards the side we removed it from. So if you remove a reactant, it will come towards the reactant side. If you remove a product, it will come towards the product side. So just to sort of visualize this, let me try a little award-winning stick figures here. So let's say we had a system that is at equilibrium. So we're at equilibrium here. And what happens is, we'll say the left-hand guy is our reactant, right-hand guy is our product. And when we add more product, so somebody hops on the right-hand side, this situation is going to occur. And to fix this situation, we need to put more people on the left-hand side. So we add it to the right, it's going to shift to the left, and it's going to be able to once again return to equilibrium at that point. So we were at equilibrium, we added, messed it up, it shifted to fix it, and back at equilibrium at that point. Now, let's say the same thing happened and this guy on the right-hand side decided he's going to hop off. When he hops off the right-hand side, this deal happens. So to fix that, we need to put more people back on the side the guy hopped off. So we're going to shift towards the side that was removed. And when we do, we once again get back to equilibrium here at that point. So when we add concentration, always shifts away, whichever side in the balance equation that guy is there. When we remove, we basically take something away. Now, adding is very simple. You can basically just take it off the shelf and add in what you need. When we remove, there's two ways we could kind of remove something. And two ways is to remove is to make a solid or a precipitate, or make something like water. And the reason why these two things work well for removing things is when we talk about equilibrium, there's really two things that are not included. And we do not include anything that's a solid or anything that's a liquid. So when we talk about this over here, the two things that are not included in the equilibrium expression is anything that has a solid or a liquid. They pretty much do not participate in the equilibrium. That means that really the only things that are included are things that have an aqueous symbol or a gas. So these are the two things that are really included in an equilibrium. Solids and liquids are not. So we could take advantage of that by making a solid or making water, which is a pure liquid, and that's one way to remove something from a solution. Obviously, if you make a solid, you'd be able to see it physically. If you make water, usually you can't really see it because it's just H2O, so it doesn't you can't really physically sort of see it, but it is one way we could remove something. So that's two stresses, adding or removing concentration. Another important sort of one is pressure and volume. And pressure and volume are basically related to each other. And as one goes up, the other goes down. So as the pressure goes up, the volume goes down. And we'll see that in the next chapter. That's what's known as Boyle's law. And vice versa, as the pressure goes down, the volume goes up. So when we're dealing with these, usually volume is a good thing to sort of look at. If the volume gets really small, the pressure goes up. And if the pressure goes up, we kind of want to bring it back down. So when we have a very small area, we need actually less gas molecules to fill it. If we had more gas molecules, pressure would continue to rise. So in that smaller volume, we need less gas molecules. And that's going to depend on the actual equation as to which side has more gas molecules, which side has less gas molecules. You basically look at the equation, look at everybody who's got a G, and you count up how many we have on each side. and whichever side has the least is the side it should shift to. The opposite is true here. If we lower the pressure, the volume is going to get larger. And if the volume gets larger, that means that we need more gas molecules, because as we lower the volume pressure to bring it back up, we need more gas molecules. More gas molecules mean more collisions. So it would shift to the side with more gas molecules. Any questions on that? So let's take a look here. So let's just say that we had 2A plus 3B goes to 4C. All right, so I'm gonna give you some examples here. You tell me what you think. Let's say we add more C, which way will it shift? To the left, right, or no change? If we remove B, which way will it shift? And if we increase the pressure here, so which way will it go? Will it shift to the right, shift to the left, or no change? So take a moment and think about what will happen in this reaction here. So if your question is, does coefficients count when you're counting up gas molecules? It does. So that's how you want to actually count them, is everybody's got a G, just count up the coefficients that are in front, and that will tell you how many total gas molecules you have, if that was your question. Okay, so let's take a look. So first off, we're adding more C. So when you look at an equation, you want to think left-hand side, right-hand side. So we're adding more C, which is over here on the right. When we add, it shifts away from the side we added it to. So it should shift to the left. So the first one should end up shifting to the left. Again, add away. So since we're adding products, it should shift away from that side and we'll shift to the reactant side. Now let's take a look at B. In case of B, we're actually removing B. So what that means is B is over here. When we remove something, it will come towards the side we're removing it, which means this will also cause the equilibrium to shift to the left as well, towards the side we removed it on. And lastly, here we are increasing the pressure. So again, we're increasing the pressure. That means the volume should be decreasing. And again, what you want to think about is small volume means less gas molecules is needed. So when we look on the left-hand side, they are both G's, they're both gases. So we have 2 gas molecules here and 3 gas molecules here, gives us a grand total of 5 gas molecules. On the right-hand side, this is a G, so there's only a 4 there, so that is 4 gas molecules. That means in this particular case, since we need to go to less gas molecules, this should shift to the right. Question on any of those examples there? Okay, so that is concentration, adding and removing. That is pressure and volume. Pressure and volume always related to each other. And again, I would relate it to volume. Kind of easier to remember. Small volume, less gas molecules. Bigger volume, more gas molecules is a good way to remember that. Another thing that affects equilibrium is temperature. And temperature works the same way as concentration. So this works the same as concentration. which means if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards. So when we talk about away and towards in the case of temperature, it all has to depend on whether it is an endothermic reaction. So when it's an endothermic, that means that heat and energy is absorbed. And because heat and energy is absorbed, it is sometimes related with a delta H, which is a positive value. And what that means is heat and energy can be thought of as a reactant. So if we were to write that into the equation, heat plus A plus B goes to C, this would be an endothermic process. Heat would be considered a reactant. And that is different than an exothermic process. In an exothermic process, heat and energy is released. Okay, so you come across a delta H, that will be a negative value. Usually negative means exothermic in terms of energy, and positive means endothermic. And what that means is if you were to write that into an equation, heat would be considered a product in that case. So if you have an endothermic process and you increase the temperature, it will shift away. So when you increase the temperature, it's like adding more there. It will cause the equilibrium to shift to the right. If you decrease the temperature on an endothermic, it will be like removing this guy. And when you remove, it will go towards the side you removed it from. And vice versa down here. If you increase the temperature here, temperature is on the product side, it will go away and it will shift to the left. And if you decrease the temperature, that is like removing heat and energy. So it will come towards that side and shift to the right. So it really depends on whether or not the reaction is endothermic or exothermic. And for our class, you'll have some information that will tell you that. Probably will just straight out tell you, hey, it's exothermic or endothermic. Or the heat will be written into the equation. Again, heat on the reactant side, endothermic. Heat on product side, exothermic. Question on temperature. The last thing is a catalyst. And a catalyst is something that we add to a chemical reaction to speed it up. It is not a reactant, nor is it a product. It is just there solely for the purpose of speeding up the chemical reaction, so of making it occur faster. So when you add a catalyst to something that's at equilibrium, it will actually have no change. So it will cause no change to occur because of that. And so that is a possible answer you could come across as a no change. Also, if you add something like a noble gas, that typically will not have an effect on equilibrium either. Again, noble gases are chemically inert. They really don't react with others. Any questions on that there? So let's take a look at some examples here. Let's say we had N2 plus H2 makes some NH3. Oops, gas. Let's go with 2, a gas, a 3, and a gas. And let's say that this is exothermic. All right, so you tell me what happens. Will it shift to the right, to the left, or no change if we add more N2, we decrease the temperature, we increase the volume, we remove NH3. Let's see here, blah, 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 blah. Let's do Let's add some H2. All right, so take a second and try to figure out what happens in each of those cases. Will it shift to the right, shift to the left, or no change if we do all these things? Okay, so let's see how we're doing. So first one, we're going to add N2. So again, add away, so AA. So N2 is on the left-hand side, which means we then should see it shift away from the left-hand side, and it should shift to the right. So again, add away is the way you want to do that. If we decrease the temperature, so the important part here is this is exothermic, which means if we wrote heat and energy into the equation, it would be a product. And if we decrease the temperature, it would be like removing this heat. And when we remove, it goes towards the side we removed it from, which means this would also shift to the right, which is the side where we removed it from. Now we're going to increase the volume. So volume and pressure are related to each other, but as we talked about, big volume means we need more gas molecules. So we want to look at the equation, and these are both gases on the left-hand side. Coefficient is 1 here, coefficient is 3 here, which means we have 4 gas molecules on the left-hand side. On the right-hand side, also a G, and we only have a 2, which means we have 2 gas molecules. That means in this particular reaction, the more gas molecules is actually to the left-hand side of the arrow, so it will shift to the left-hand side in this particular case. Any questions on that so far? Okay. So looking at NH3, which is here, we're going to remove NH3. So when we remove, it goes towards the side we removed it from. So it should shift to the right. And lastly, we're going to add H2, which is on the left-hand side. When we add, it goes away from it, which means it will also go to the right. Any questions on that one there? Okay. Let's try another one here just to make sure. Let's see, let's go with N2 plus O2 gives us 2NO. And we'll do endothermic on this one. Why not? Endothermic. So let's say we increase the temperature, increase the pressure. Let's say we added more NO. We removed O2. we added a catalyst. All right, so same thing, see what happens. Does it shift to the left, shift to the right, or will there be no change in this particular cases or some of these? Okay, so let's take a look here and see how we did. So if we increase the temperature, so again, this is important for temperature. So it's endothermic, which means heat would be on our reactant side. So if we increase the temperature, that would be like adding more heat. And again, when we add, it is going to shift away, which means it will go to the right-hand side there. So we'll shift to the right in this particular case. If we increase the pressure, again, if we increase the pressure, the volume will go down. And again, in a smaller volume, we need less gas molecules. And if we look at the equation here, reactant side, there is a grand total of 2 gas molecules, 1 on each of these guys. And on the product side, we got a grand total of also 2 gas molecules. That is what we call a tie here, and that means no change is going to occur because there is no side that is more or less, so it's not going to actually affect it at all because of that. So we got equal amounts on both sides, so it doesn't need to go either way, and it will basically have no change occur. So again, that's another common way that you could kind of get no change, have a tie on both sides in terms of gas molecules, so there is no more or less. If we add NO, so we're adding NO, which is on the right-hand side. So when we add, it goes away from the side we added it to. So it should go to the left in this particular case. If we remove O2, which is right here, when we remove, it goes towards the side we removed it from. So it should end up going to the left as well. And lastly here, when we add a catalyst, this will give you no change. You'll just get to the equilibrium a lot faster, but it will not cause it to shift either way. Any questions on those there? Our Le Chatelier's principle in general. Now, obviously, when we kind of think left and right, there is no left and right when everything's in a beaker together. So just so everybody's clear, in the beaker, you pretty much will have everything floating around in there. So for example, if these were all aqueous guys, we'll pretend, are in this flask, or this container, you have all these guys floating around together. So there really is no left or right when we talk about sort of really is happening, but we talk about left or right in terms of the actual balance equation. So that's a good way to sort of think about it that way. Any questions on Le Chatelier's principle or anything like that? All right, that wraps up chapter 5. So we're going to go off to chapter 6 now. So just give me a second to get that all up. That one there. And where'd it go? There it is. Okay. Yeah, give me 1 second here. Okay. All right, so we are going to talk about chapter 6, but here we'll do one more example here before we jump into that, I guess. There we go. Where are we at? There, grab a pen. All right. We'll just borrow the front page here. So let's say we had, H2 plus O2, H2O. All right, and let's just say this is, we'll make up something. We'll go with endothermic for the sake of this made up example here. So let's say we added H2O. Let's say we removed O2. Let's increase the temperature. Let's decrease the volume. And let's see here. Let us also add some H2. All right, which ways will it go here in this case? What you come up with? Okay, let's take a look then. Here we're adding H2O, so add away. So our water's on the right-hand side, which means it should shift away from that side and go to the left in that particular case. We're going to remove O2. So when we remove, it goes towards the side we're removing. So since we're removing over here on the left, it also should cause it to shift towards that side, and we should see it go to the left-hand side, more reactants being made. Increasing the temperature, again, going to be based off of exothermic or endothermic. So in this made-up example here, I went with endothermic. So that means heat would actually be considered a reactant. And if we increase the temperature, that's like adding more heat. So we're going to add, so again, add away. So heat is on the left-hand side. When we add it, it should shift away from it, which would cause it to shift to the right in this particular case. When we decrease the volume, we have a smaller volume. Pressure goes up. And what we want then in a smaller volume is less gas molecules. So on the left-hand side, we have a grand total of 2 and 1 is 3 gas molecules. On the right-hand side, we have 2 gas molecules. That means in this case, it should shift to the right because it has less gas molecules. And lastly, we're adding H2. H2 is on the left-hand side. Again, when we add, it goes away. So since it's on the left-hand side where we're adding it, it should shift away from that side and go to the right-hand side in that particular case. Any questions on that one there? Okay, so again, the best thing to do is kind of look at it. You're welcome. And, think about the equation as left and right and just make it very simple. If you add away, so whichever side you added it to, shift it away from there. If you remove, it comes towards it. And that's just an easy way to remember it. Look at the equation for the left and the right. All right, other questions on that there? Okay. So switching gears here, we're going to talk about gases and gas laws here in chapter 6. So let us get going on that. By the way, everything looks okay. It's big size, not small or anything, I hope. Yes. All right. If it is small, let me know in the chat or something so I know. So let's talk about gases and things that exist in the gas phase. So when we talk about sort of normal conditions and sort of room temperature conditions, if you will, what we're really referring to is a pressure of 1 atm. ATM is an atmosphere. That's a unit of pressure. And 25 degrees Celsius is sort of normal, run-of-the-mill, standard room temperature, if you will, conditions. Things that are ionic compounds really do not exist as gases. And they don't exist as gases because ionic compounds are a metal and a nonmetal. And the metal is a cation, which is positively charged. The nonmetal is an anion, which is negatively charged. And that is that electrostatic attraction, which is a super strong attraction. Again, remember, electrostatic attraction is what's considered a intramolecular force within a molecule. And those are always stronger than an intermolecular force. So it's a very strong force. And under normal conditions, salt, for example, sodium chloride, doesn't exist as a gas because to sort of overcome that really strong force, you would have to put a lot of energy in there, and it just doesn't normally happen under normal conditions. So that's really good, right? Because otherwise, if we put salt like on our fries that were hot and it could go really easily into the gas phase, we would have like chlorine gas and stuff on our fries, which would probably not be a good thing or anything like that. So ionic compounds typically will only melt. So if you ever heated an ionic compound or done an experiment where you evaporate off water and you continuously heat it, you'll be left with a solid. And if you keep heating that solid, you can heat it all day. It pretty much will not go into the gas phase. It will just start looking like it's starting to melt a little bit along the way. So ionic compounds really don't exist as gases under normal conditions. But covalent compounds or molecular compounds are different. So these are the guys that will be sharing electrons. And as they share electrons, these covalently bonded guys, they actually do come as gases. So some like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia is a gas, NH3. Methane, which is the simplest organic molecule, is also a gas. But a lot of molecular compounds are liquids or solids at room temperature. But the difference is they can be converted into a gas much, much easier. And a prime example of that is water. So water, which is a molecular compound that is polar, negative, positive. When another water is attached to it, that's also negative and positive, it's able to do some hydrogen bonding here. That hydrogen bond is an intermolecular force. And what that means is that force is not as strong as an intramolecular force. So unlike an ionic compound where you got to try to break apart all the individual elements from each other, and that just doesn't happen, in a molecular compound like water, when we start to heat it, we have enough energy to break apart that intermolecular force, and we end up with one water molecule as a whole and another water molecule as a whole that's able to break apart into the gas phase. That's what happens when we boil water, right? We heat it up. We have enough energy to break apart all those water molecules, and before you know it, you have all these water molecules that are gases, which is the steam that comes out of water as you're heating it, and they're able to basically break apart. Again, because hydrogen bonding is a strong intermolecular force, but that intermolecular force is much weaker than a intramolecular force like ionic bonding or electrostatic attraction, or even covalent bonding as well. So what substances are usually found as gases under normal condition? Here's a list of some of those. A lot of those diatomic elements or diatomic molecules that are elements: hydrogen gas, oxygen gas, nitrogen gas. Fluorine is a gas as well, and chlorine. Ozone, which is O3, that's also a gas, good in some parts of the atmosphere, not so good in other parts. Why we run our sunblock and all that kind of stuff, especially with UV and all that coming through. But ozone affects certain things. And obviously on our periodic table, our group 8, which is our noble gases. And those are monoatomic gases. That means they come as ones. So helium, neon, argon, krypton, they come basically as ones. So on the periodic table, again, these guys kind of in the purplish over here. These are all gases under normal condition. And again, these are our diatomic guys here. And our noble gases, which are monoatomic, coming as one. So this is a good time, again, to talk about difference between two words that are commonly used and sometimes kind of used interchangeable, even though they really do mean sort of two different things. And that's a gas versus a vapor. So when we talk about a gas, that is a substance that under normal conditions is found in the gas state. And that is different than a vapor. A vapor is basically the gas form of a substance that under normal conditions is either a liquid or a solid. So the prime example of that is what I was just drew on the last slide, which is water. So under normal conditions, H2O is found as a liquid, right? Coming out of our pipes and all that good stuff. But you can very easily convert water into a gas by heating it up. And that's why when we see water in the gas form, we oftentimes refer to it as water vapor, because normally water is a liquid, but it can be in a gas form. And again, that's why we call it water vapor rather than water gas, because that just sounds kind of funny when we say water gas. But that's why we really call it water vapor, because in normal cases, it is found as a liquid. And that's different than, say, something like methane, for example. Methane is normally found as a gas. So we call it methane gas, not methane vapor, because, again, not normally found in a different state. So when we talk about gases, there's really a couple of major sort of properties that we deal with when we talk about gases, and that is pressure, volume, and temperature. So PV and T, if you will, pressure, volume, and temperature. And one major aspect of gases is the units of pressure. And a barometer is a instrument that measures atmospheric pressure. As we'll see on the next page, it basically is a pool of mercury, and the atmospheric pressure basically beats down on it, and the mercury basically rises in the tube, as we'll see a picture. And these are some 3 common units of pressure: ATM, which is an atmosphere; TOR, which is torr, named after our good guy here that invented the barometer; and mmHg, that actually stands for millimeters of mercury, which is Hg. And that is because years ago, before they started taking them out of everywhere, barometers were made out of mercury. And there's basically pools of mercury. And on the little tube, there would be like a ruler. And oddly, you would read the ruler like in millimeters. And that's where that name comes from, basically millimeters of mercury, reading basically where the mercury is in that sort of ruler on the tube. Now, this is important conversion factors here. 1 atmosphere is equal to 760 millimeters of mercury, and that equals 760 torr. 1 torr is the same as a millimeter of mercury. It is a 1-to-1 relationship. So this conversion is used a lot here in gases. If you have atmospheres and you want either millimeters of mercury or torr, you would multiply by 760. Again, torr or millimeters of mercury, same unit basically, 1-to-1 relationship. Or if you have torr or millimeters of mercury and you want atmospheres, you divide by 760. So your 760 is a really important number there. It is the conversion between really the 3 common units that are used in gases: atmospheres, torr, and millimeters of mercury. There are definitely other units of pressure, things like pascals, kilopascals, bars, PSI, pounds per square inch. But probably in our class and in terms of chemistry, atmospheres, torr, and millimeters of mercury are probably the 3 units that you will see the most. Any questions on that conversion there? Here's a much prettier picture of a barometer. Almost looks like my bad drawing, but basically a classic barometer was a pool of mercury with some mercury in a glass tube. And again, as the atmospheric pressure exerted on it, the mercury would rise, hence the saying mercury rising, right? So there's that mercury. Mercury is a weird one. It has actually an inverted meniscus going in the opposite direction. You actually read it from the top of the meniscus like so. And again, like I said, on this tube, usually there's like a ruler and you kind of measure it in millimeters of mercury to get your reading. Most of them have been taken out of like schools and stuff like that because it contains mercury, and they've been replaced more as kind of like alcohol sort of barometers and stuff like that. So we're going to talk now about some different gas laws. And as I mentioned before, a lot of the relationships we're going to look at involve pressure, volume, and temperature. So the first relationship we're going to look at involves pressure and volume. We're going to keep temperature constant. And this is what is known as Boyle's law. And Boyle's law basically states that the volume of a fixed gas maintained at constant temperature is inversely proportional to the gas pressure. And this is Boyle's law relationship. This is P1, V1, that's pressure, and that's volume, kind of like before, if you will, conditions, and our pressure and volume after sort of conditions. In terms of pressure here, the pressure can be any unit you want, as long as they are the same on both sides. So atmospheres, millimeters of mercury, torr and torr. Volume, same deal. Can be any unit you like as long as they are both the same unit. So it could be liters on both sides, could be milliliters on both sides. The relationship that we see with Boyle's law is what we were just talking about with our Le Chatelier's principle. As the pressure goes up, the volume goes down. And this is because when you have a small volume, the gas molecules are flying around in this very small area, which means there's going to be more collisions. More collisions results in a higher pressure. That's essentially what causes the pressure, is all those collisions. So smaller volume, they have nowhere to go. They're just going to continuously bang into the container, bang into each other as well. And that's going to cause the pressure to increase. And the opposite is true. As the pressure goes down, we see that the volume goes up. And that is because in a bigger area, there's a lot more room for gas molecules to fly around, which means it's going to take longer for collisions to occur. The longer it takes for collisions to occur, less collisions, and we will see the pressure start to decrease. So basically, as one goes up, the other goes down. So that is like basically Boyle's law relationship. One goes up, the other goes down, and that's what inversely proportional basically means. And here's a plot of that. What we see is pressure versus volume. So here at very small volumes, we have large pressures. And at larger volumes, gives everybody a little bit more room to fly around, we see that the pressure starts to drop. So again, that sort of opposite relationship. So why don't you try one here? An inflated balloon has a volume of 0.55 liters at sea level, which is 1 atmosphere. It goes to 6.5 kilometers, where the pressure is 0.4 atmosphere. Assume that the temperature remains constant. What is the final volume of the balloon? So give it a go, and we'll talk about it as soon as I find a calculator, maybe. Okay, so let's take a look here. So I highly recommend when you're doing sort of gas laws, we're going to talk about a bunch of different sort of gas law formulas that you'll need to know. So sometimes it's best to kind of pull out the information from the problem. And a lot of times when you do that, you'll almost be able to kind of see the gas law you should use. So if we go through this problem here, we have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is useless information. And we have another pressure, which is 0.4 atmospheres. And we're looking for a volume. So again, even if you weren't sure where to start, since we only learned one equation so far, P1 V1 equals P2 V2, you could really kind of see the equation or formula there. Typically, people just label the first guy's ones, the second guy's twos. So in this case, we do want to solve for V2. So opposites when we go across an equal sign. So even though it's not a fraction, P2, V2 is like on top. So we're going to divide the P2 to the other side. Those guys are going to cancel. And that will give us P1, V1 over P2 equals V2. Putting in our numbers, P1 is 1 atmosphere. V1 is 0.55 liters divided by our P2, which is 0.4 atmospheres. Atmospheres will cancel. It's going to leave us with liters, which is good because that's what we're looking for. So 1 times 0.55 divided by 0.4 gives us a 1.4 liters as our answer. We could also see it doesn't make sense. So when we look at our pressure in this case went down, which means our volume should go up. And it went from 0.55 to 1.4. So it does make sense. And that's why it's good to sort of think about those relationships as you're doing these problems to make sure your answer does make sense. Any questions on that one there? All right, let's try another one, which is a sample of chlorine gas occupies a volume of 946 milliliters at a pressure of 726 millimeters of mercury. What is the pressure? What is the pressure in atmospheres? Why don't we do that? If the volume is reduced to, we'll go with 154 milliliters. Let's see what you come up with on this one. Okay, so let's take kind of the same approach. So we definitely have a volume that is 946 milliliters. We have a pressure that is 726 millimeters of mercury. We're looking for a pressure, and we have another volume of 154 milliliters. Again, you could almost see Boyle's law kind of when you pull out that information. So here we're going to solve for P2 in this case. So P1 V1 equals P2 V2. Again, dividing the V2 to the other side, those guys will cancel. That gives us P1 V1 over V2 equals P2. Putting in our numbers here, our P1 is 726 millimeters of mercury. Our V1 is, we got there, 726 and 946 divided by our V2, which is 154 milliliters. Milliliters will cancel. That's going to leave us millimeters of mercury that's left over. And if you do all that, 726 times 946 divided by 154 gives you something like 4460 millimeters of mercury. By the way, 3 sig figs off of all three of these guys are 3 sig figs. We do want to go to atmospheres though, so that means we should take the 4460 atmospheres, and we want to, I'm sorry, that's millimeters of mercury, sorry. Try that again. 404,460 millimeters of mercury. We want to divide by 760 millimeters of mercury is 1 atmosphere. Again, that's the conversion we saw earlier. So we're going to divide it by 760. Going to get us something like 5.8. On my calculations, I really didn't round. 5.87 atmospheres. And 5.87 atmospheres would be our answer here. By the way, up here was 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs on that number as well. Question on Boyle's law here. We again see the trend that we saw. Volume went down. Pressure went way up. Yeah, it went to 4460 from 726 in that particular case. Any questions on that there? Okay. So the next sort of relationship we're going to look at is Charles' law. And Charles' law dealt with volume and temperature holding pressure constant. And we get V1 over T1 equals V2 over T2. And this is what's known as Charles' law. And if you look at the temperature does need to be in Kelvin. So no matter what gas law you're dealing with, if you have temperature, Kelvin is pretty much what it needs to be in. And the reminder that the temperature in Kelvin is 273 plus the temperature in Celsius. So you want to add 273 to it. Volume here can be any unit you like, as long as it is the same unit on both sides. The relationship here is this: it keeps constant pressure, which means if you increase the temperature, all the gas molecules can gain more energy. They're going to fly around a lot faster, going to have more collisions, and the pressure should go up. So in order to keep the pressure constant, what happens is as you increase the temperature, the volume increases with it. And when the volume increases with it, it gives everybody more room to move around. So even though they're moving faster, they have more room to fly around in, causing the collisions to maintain where they're at. So the relationship here is as the volume goes up, so does the temperature, and vice versa. Temperature goes down, volume will go down with it. Again, if you lower the temperature, all the gas molecules can fly around slower, going to be less collisions. So the pressure would normally start to drop. So to keep it constant, the pressure, the volume gets smaller. So even though they're moving around slower, they're in a very small area. So they're going to keep the collisions up and the pressure happens. There's also a relationship which is known as Guy-Lussac's law. And that is P1T1 equals P2T2. And this is at constant volume. Same thing here, temperature needs to be in Kelvin. Pressure can be any unit you want as long as they are both the same on both sides, but the temperatures do have to be in Kelvin here. And because this is at constant volume, what happens is as we raise the temperature, the volume is not going to change. So it's fixed. And that means as we raise the temperature, gas molecules are going to fly around faster. We're going to have more collisions. And what we will see is the pressure will start to go up. So in this situation, what we end up with is as the temperature increases, so does the pressure. And as the temperature decreases, so does the pressure in this situation. So these are two gas laws which are very similar to each other. Basically, the relationship is as one goes up, one goes up, and as one comes down, one goes down with it. So Charles' law, V1 over T1 equals V2 over T2. Guy-Lussac's law, P1 over T1 equals P2 over T2. Any questions on that there? Okay. So let's try one here. Make sure math-wise we're okay. Actually, let's take a look first at this graph. This is a graph of volume versus temperature for a bunch of different gases. And if you take all these lines and you take them all back to the temperature line, they all hit the exact same spot, which is minus 273.1 degrees Celsius. Kelvin realized that and called that absolute zero, because if we convert this into Kelvin, plus 273.15 gives us 0 Kelvin, which is absolute zero. So that's why pretty much in gas laws, when we have temperature, it does need to be in Kelvin for sure. So even if it gives you the temperature in Celsius and asks you to give the answer in Celsius, you need to convert it to Kelvin, do the problem, and then convert it out of Kelvin. But we do see what we talked about here. At high temperatures, we have large volumes, low temperatures, small volumes. All right, so give this one a go here. In an experiment, 452 milliliters of a gas is used in a light bulb that's heated from 22 degrees Celsius to 187. What is the final volume in milliliters? Okay, so since we're getting to the end here, let's take a look. I would follow the same approach. So I got 452, which is a volume. I have a light bulb that went from a temperature of 22 degrees Celsius to a temperature of 187 degrees Celsius, and I am looking for a volume. So if you look at this, this should definitely kind of point you in the right direction. Clearly, Boyle's law would not be good for us here because there's no pressure. So we definitely would want to use Charles' law, which is V1 T1 over V2 T2 there. And we do need to do a couple things here. We do need to change our temperatures into Kelvin. So we're going to want to add 273 to each of them. And when we do that, 187 plus 273 gets me 460 Kelvin. And 22 plus 273 gets me 295 Kelvin. My volume is okay. So in this case, I have everybody except V2. So again, we need to go opposite. So I need to move the T2 to the other side. When I move it to the other side, it ends up in the opposite location. It's on the bottom on the right. It will end up on the top as you go across. So if I do that, I will end up with T2 V1 over T1 equals V2. So again, when you go across the equal sign, opposites work, ends up in the opposite location is an easy way to remember that. That also means we want to put the right numbers in the right spot. So 460, which is my T2, should go up on top. V1, which is 452, and my T1, which is 295 Kelvin. Again, the Kelvins will cancel. Gonna leave me some milliliters, and we will end up with 705 milliliters in this particular case. And we do see the trend that we talked about. Our temperature went up, so our volume went up as well. So we can see that relationship here with our answer. So it does make sense in this particular case. Any questions on that particular one? All right, so you do need to obviously know these gas laws. We're going to talk about some more next time we lecture. A reminder that this Wednesday is our first exam. You'll take it like you did with the quiz using proctorial. It will start, I'm going to think it's going to start officially around 5:30, but it may start a little bit earlier in case, again, you want to kind of start it a little bit earlier so you don't feel so rushed to get the lab. I will let her know. Obviously, we were taking an exam on Wednesday, so she'll have an idea. But you won't get any more time, obviously, than what everybody gets. But in case you don't want to feel so rushed going from this to that, it might open up just a little bit earlier than that to kind of get you through it. You'll have the same ideas what you had to do with the quiz. You'll have like the academic honesty agreement. Again, the exam will be part multiple choice. First part, all multiple choice questions. Don't have to upload any type of work or show any work. The second part will be a written part where some of those questions you will need to show work, and you do need to upload your work at the end of the module as well. So kind of like the proctorial thing. So at the end, you'll be able to upload your work. You will be provided a periodic table, maybe some conversions and that type of stuff. A reminder that it is closed book, closed notes, and you do have to use proctorial. And as I mentioned before, try to get it so I can see at least you and your work area in your paper. Again, from my experience, maybe sitting to the side of your computer and your webcam sometimes is very helpful for that, kind of push it out a little bit and stuff like that. No, there will be a periodic table that will be part of the exam, and it will be a PDF file as well. So what you can do is click open the PDF file and flip back and forth and take a look at it and use that one that's included on the exam. So that's usually the easy way to do it. You will need scratch paper. It doesn't matter what kind of scratch paper, as long as it's clean. There's no notes or formulas or anything like that on it, obviously. And then you will, like I said, there will be some questions where you will need to upload that work. So I could give you partial credit in case something goes bad. So you'll have to upload that work and stuff like that. Other questions on that? Off the top of my head, I don't think there's going to be any formulas that are going to be given to you on this particular one. Um, so not that I know of. I don't think so off the top of my head. I'll double check. But whatever it says on those review sheets that's on Canvas, it will tell you what you can, what you'll be given for sure. So if it says you'll be given something on that, it will be given to you. Yeah. So for the next lecture, there is no lecture, so you don't have to come to Zoom. You just go to Canvas, and like I said, I might open up around 5:15 or something like that, just to give you a little extra time so you don't feel so rushed or anything like that. And yeah, you just go to Canvas, just like you took the quiz. And again, you need to use Chrome, the extension, and it should not ask you for any type of code or anything like that. If it does ask you for a code, then that means that something's not installed right. So make sure you fix that. And like I said before, if you can, to the best of your ability with whatever you're using, your laptop, your computer, your webcam, whatever it is, again, maybe sit to the side, push it back, something like that. I want to see more than just the top of the head. Yeah. So I like to see kind of you and your work paper area or something like that. You know, so do your best to do that. Like I said, I've given a lot of them, and I know it definitely is possible. So it may require you to kind of sit to the side or move it to back or something like that. So try to do your best to do that. So in terms of lecture, there will not be a lecture on Wednesday. You're just going to take the exam. The exam will be scheduled for the entire lecture period. So you'll have about whatever it is, about an hour and a half to take it. So about 90 minutes or so. And then obviously you could go to lab afterwards. Yeah. So again, do your best. So you get the idea. So it's not like, you know, all I see is like this part of your head. Yes. So do your best. And I know it's possible. Yes. So, you know, push it back, move it to the side, your laptop, and kind of look at it as a side. You can maybe get a better angle. So just try to do your best, the best that you can do. Don't break anything or anything like that, or hang anything off the roof. But you get the idea. So I'm not looking at just lights, yes, or something like that. So, you know, sort of you and your area the best that you can do. Apparently, I'm seeing in the chat that apparently lab has been canceled, I guess. Yes. I'm not sure why, but if lab has been canceled, I don't know why that would be. So if you like, since lab is canceled, I will put the link for discussion. If you want to come into discussion, you can today and ask questions. If you have questions, might be good for the exam on Wednesday as well. Those that have discussion today, you obviously should come to discussion. But if you like those people in the other class, I'll put the link for today's discussion up in just a second when we're done here, and you can pop in there if you have some questions and stuff like that. Okay. All right. I think I got everybody's questions. So if not, if you're going to come to discussion, if you have lab today, since it's canceled, like I said, give me a second, a minute or two, and I'll pop the link up there in case you have some questions about the exam or something you want to do that. And those people that have discussion today, we will obviously answer any questions that you have for the exam and stuff like that. All right. So make sure you do put here in the chat if you haven't done so, and give me, again, like I said, a couple minutes. I'll put that link up there in case you want to come if you're not normally coming to discussion today, and if you have some questions or something I could help you out with. All right, I'll see everybody. Why don't we start discussion about 5 minutes or so, okay? All right.